Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the first continuation of the lecture entitled A Gentle Introduction to Infinite Series Solutions for Differential Equations. When last we spoke, we were charged with doing this problem. I hope you did it, but just in case you didn't, I'll give you a chance to do it now. You know what to do. Let's see how you did. So we want to start the series at 5. So all we need to do is notice that this means we will increase the starting point by 2. And that means all the other ends will need to decrease by 2 to keep the series to be the same. Doing this for the series will give us this as our answer. Now here are two problems, and the directions ask us to write each of the following as a single series in terms of x minus x0 whole to the n. So here in the part A, we're talking about x minus a minus 2, and in problem B, we're talking about x minus 3. And we want those to be written as a single series in terms of x minus x0 to the n. You know what to do? Let's see how you did. So here's the problem that we're working with. So there are two series here, and the instructions ask us for one, and eventually we want to subtract the two series. But much work has to be done to prepare them for the subtraction. That means you can't do this until you've dealt with the coefficients in front of them, and they will need to start at the same value of n, and they will need the same exponents on the x minus x0. We almost always want to take care of the coefficients first, so we're going to take this x plus 2 whole squared and we'll distribute it in here, and we will end up with x plus 2 whole to the n minus 2. And the second one for now remains the same. Now we need to take care of the index shift on each of these series. The exponent on the first series needs to go up by 2. So we'll shift the series down by 2. So we go down by 2 in the index and up by 2 inside. And now we have x plus 2 to the n. On the second series, we need to shift, here's the second series, we need to shift down by 1 with the exponent, and that means that we're going to shift the index up by 1. Again, it must balance. So now we have this expression. Now we're still not there, but we've got the exponents being the same. And notice that I have n minus 1 here, and n minus 1 would be 0 when n equal 1, so I'm going to be easily able to change this to summation n equal 1 to infinity without changing anything, because that is a 0. And that's what I did here. So now this starts at 1, this starts at 1. They both have x to the n, so now we can combine these by combining the coefficients. Or you might want to think about, I'm going to be factoring the x plus 2 to the n out of there and moving it inside the sum. But you see, this is what I get, and now we have finished this example. Let's look at the second example. In this, the main issue is the fact that we can't just multiply the coefficient into the series, because we have x minus 3 in here and we have x here. Therefore, the first thing we need to do is correct the coefficient so we can bring it into the series. And we do it by using that great technique of adding 0 in a clever way. So we have x here, and we're going to write x as x minus 3 plus 3. And now we're going to distribute this. So first we distribute the x minus 3 times all of this business, and then it's going to be plus 3 times all of this business. Make sure you follow the steps. And now we can move this coefficient into the series, and we'll end up with x minus 3 raised to the n plus 4. And here we just have a 3. We can move the 3 inside of there. Now we need to get the exponents to match. So here we have n plus 4. We have n plus 3, but we want to have n. This means we have to shift the first series up by 4 on the index, so we can shift the n down by 4, and we get this. On the second one, we need to do a shift as well. So on the second one, what we're going to do is we can't just start this at n equal 3 because there isn't an n equal n minus 3 here. And so what we're going to do is we're going to strip out that n equal 3 term, and we're going to start this at n equal to 4. So we're stripping out the n equal 3 term, and we're going to have both of them starting at n equal 4. So we'll have this, and then that first term. And so then I can combine these, and that's the best that we can do. Let me close with another fact, and the next fact is that in order for a plus bx plus cx squared to be equal to 0 for all x, we're not solving this for what x, for all x, the only way that can happen is for a, b, and c to be all equal to 0. We have a similar fact, and we're going to use this for power series. If we have the summation of n goes from 0 to infinity of an times x minus x0 to the n, and x of course is not x0, this is all equal to 0, then all of those coefficients are equal to 0. We will use this fact. Now I'm going to talk just briefly about a Taylor series. We talked about a power series, which is a function of x. A Taylor series is also a power series, but you start with a function f that is infinitely differentiable, and we talk about finding its Taylor series about x minus x0. Well, if you're doing that, one of the things you learned was that f of x is equal to, since this is infinitely differentiable, these are the Taylor coefficients. And this will be the Taylor series. And when you have f to the written to the 0 like this in parentheses, that means the 0th derivative, and when you put it in parentheses, this is the nth derivative. Although not so much in Chapter 6. In Chapter 4, nonlinear considerations, we've already talked about that. And again, in the numerical techniques near the end of our course, we will encounter Taylor expansions. And sometimes, even in Chapter 6 considerations, it's useful to recognize them. I'm reminding you of a few that you have. But first, there is a definition. A function f does not always converge. Its Taylor series does not always converge to f of x, but if it does, it is called analytic. We will use this definition later in Chapter 6, and here are some Taylor series that you want to remember. If you have e to the x, its Taylor series is this, and it converges for all x. Now, if we change the point that we're expanding the Taylor series about, instead of expanding it about 0, if we expand it about minus 4, we will get this. Notice the coefficients change. If we expand the cosine of x about x equals 0, this is what we get. Remember that the cosine was an even function, and we're only using the even powers of the infinite series. For practice, you might want to verify that this Taylor series for sine is this. Again, the sine is an odd function, and we only get the odd powers here. And it maybe is interesting to see that even if you have a polynomial that is finite, if you're expanding it not about x equals 0, but about x equal 2, it looks different even though it is the same representation. This discussion will continue in 24.2.